Okay. Are you there? Am I audible?
Yes, yes.
Okay, so last class we were doing mass spectrometry and we solved a few questions. Let's solve a little more so we can revise it as well and then we move on. So we did this question for iron. Then we did this question for chlorine. Okay. Now let's do this question. It's a bit different. It has all the concepts in it together. This is question number 3. Question number 3 states, the mass spectrum for rubidium is given below. What isotopes are present in rubidium? Part B asks, what is the percentage abundance of each isotope? And part C says, calculate the relative atomic mass of rubidium. So these 3 questions have been given to us with this mass spectrometer graph. Here we have mass to charge. Here we have percentage abundance. Here we have relative abundance. This is what they've given us in the question. And part A is asking, okay, do you want to revise the mass spectrometer thing or do we just start with the question?
Can we revise first?
Sure. ठीक है. So a mass spectrometer tells you 3 things, right? The number of different peaks, the number of different isotopes. So how do you know the number of different isotopes present in a sample? For example, we're looking at this mass spectrometer graph. So looking at the number of peaks, we can know the number of isotopes present. So this has 4 peaks, 1, 2, 3, 4. So we can say that iron has 4 isotopes present, right? And if I want to know the isotopic masses of these 4 isotopes, I can just read the mass to charge ratio. So I can say the first isotope is iron 54. Then I can say the second isotope is iron 56. Third one is iron 57. And the fourth one is iron 58, right? So we can know the number of different isotopes, we can know the relative isotopic mass of each atom, and we can know the abundance of each isotope in the sample. How can we know the abundance? Through the y-axis. So here we can easily say that iron 56 has the highest abundance. And the lowest abundance is of iron, 58, because the y-axis is showing you percentage abundance, right?
Yeah.
Okay. Now what goes inside the mass spectrometer? Mass spectrometer के अंदर goes a random sample. And this sample goes through 5 processes: vaporization, ionization, acceleration, deflection, and detection. This sample first turns into a gaseous state, which is why the first process is vaporization. Then ionization, M turns into an M plus ion, which is a molecular ion. Pair acceleration due to the negatively charged plates, then deflection due to the magnetic field, and then detection. Okay. Now coming back to the question, what isotopes are present in rubidium? So what can be the answer to this question?
There's 2 isotopes.
Yes. Which one?
Rubidium,
Yeah, rubidium, but which one? What are the isotopic masses?
85 and 87.
Perfect. So we have rubidium 85 and rubidium 87, because they're asking us what isotopes. They're not asking us how many isotopes. Okay, so give the complete answer. The right answer is 85 rubidium and 87 rubidium. Part B asks, what is the percentage abundance of each isotope? They're asking us the percentage abundance. And what do we have on the y-axis?
Relative
Exactly,
abundance.
relative abundance. So relative abundance may we can see that rubidium 85's abundance is 7. And rubidium 87's abundance is 80. And total abundance of both of these combined is 18 plus 7, which is 25,
25.
right? So if I were to write both of these as a fraction, I can say rubidium 85's fraction is 7 over 25, and rubidium 87's fraction is 18 over 25, right? Now doing some math, I can convert this fraction to a percentage. And how do I do that? I will just multiply this by 100, right?
Yeah.
So the answer that I get here for rubidium 85 is 72%. And for rubidium 87, I get a 28%. So these are the percentage abundances for the 2 isotopes. Part C, calculate the relative atomic mass of rubidium, which is the AR of rubidium. So we're going to use the same formula. This one, AR equals percentage abundance of one isotope into the isotopic mass of one, then a percentage abundance of the other one into the isotopic of the other one, and then so on. We're going to copy this formula. So percentage abundance for 85 is 72. And what's the isotopic mass?
85.
85. And for 87 is 28%. So AR here turns out to be 85.6. Is this clear?
Yes.
Okay. Question number 4. Using the relative atomic mass of bromine, which they've given to us as 79.90, calculate the relative isotopic abundances of Br79 and bromine 81. And they've also given us the isotopic masses. Okay. So this is the question. How do you think you can go about this question? They've given us the AR for bromine. They've given us isotopic masses. Yeah. Can you hear me?
Yeah.
Okay. So how do you think you will go about this question? Just a wild guess.
— 100 subtract 79.90
From
from the AR of bromine.
AR of
One-
bromine is 79.9. This is the AR. So in the past questions, in the previous questions, they have been asking us for the AR, right? But in
Yeah.
this question, they've already given us the AR. So this formula, they've told us this part from this formula, right?
Yeah.
Look. Now, if I start inputting whatever they've given us, what do I come up with? AR they've given us as 79.9, right? I've inputted this value. Percentage abundances are what we need to calculate, right? Calculate the relative isotopic abundances. Exactly. They've told us to calculate the relative isotopic abundances of Br79 and Br81. So these two are what we need to find out. And they've also given us the isotopic masses. So 79 Br, let's take this bracket and let's make this bracket for 81 Br. So isotopic mass for 79 Br has been given to us as 78.92 and for 80.9. 80.92. Now we are left with inputting these two values, percentage abundances for both of these. Now we know, okay, whatever the percentage abundance is, two percentage abundances, for example, 79's percentage abundance plus BR 81's percentage abundance is going to give us a total of 100%, right?
Yes.
So if I consider BR 79's percentage abundance to be X, 81's percentage abundance can be 100 minus X.
Yeah.
And still both of these should be giving me 100%, right? So I can use just one variable, one unknown variable in my whole question to solve this. Okay? So 79 BR की abundance can be taken to be X, and the other one can be taken to be 100 minus X, right?
Yeah.
So I'll just write X here and $100 minus X here. So yeah, abhi tak, is it clear?
Yes.
Okay. Now we'll just solve this equation. And X will turn out to be 51%. So this 51% is the percentage abundance for bromine 79, right?
Miss, how'd you get 51%?
Do the math. Do you want me to solve it?
Yeah.
Okay. So you take 100 to this side. 79.9 into 100 gives us 78.92x. I just multiplied both of these together. Plus, now multiply this as a bracket. 8092 into 100 minus 80.92x. Bracket closed, right? And then this turns out to be 78.9x plus 8092 minus 809x. Then you put all the numbers on one side and all the variables on one side. So this should be now I'm going to solve it. And 102 divided by 2. Minus minus gets cancelled. X turns out to be 51. Okay?
Okay.
Okay, so this is much more of a math question than a chemistry question, but this is from the past paper, so this can show up in the paper as well. So X turns out to be 51. So if X is 51 and X we had taken to be BR 79's percentage abundance, so BR 81's should be 100 minus X. And 100 minus 51 is 49%. And 49% is the percentage abundance for bromine 81. Right?
Yes. But Miss, I have one question.
Yep.
How do you know for which bromine you put X and which one do you put 100 minus X?
Look, they've given you percentage abundances. They've given you isotopic masses for both of these, right?
Yeah.
So I just said, okay, this bracket, I'll take it to be BR 79. So I inputted BR 79's isotopic mass here, 78.92, right?
Yeah.
So 78.92, if this is 79 BRs, I put an X here. I can also put an X here. It doesn't matter if I put an X here or an X minus 100 here. Okay? But I should remember that I used X for bromine 79's percentage abundance.
Okay.
Because this bracket is what I assume to be bromine 79's. And this second bracket is what I assume to be bromine 81's. So I put 80.92, which is bromine 81's isotopic mass, right?
Yeah.
So remember where you're putting which isotopes, isotopic mass, okay? Don't
Okay.
mix up both of these.
Okay.
Okay, one last question. So this is our question. And the question says that a sample of carbon consists of isotopes carbon-12, carbon-13, and a sample of oxygen consists of isotopes oxygen-16 and oxygen-17. Write down the formula of all the different CO2 molecules from these samples. Which molecule has the largest mass? So they're basically asking us to make combinations of a CO2 molecule. How many atoms does a CO2 molecule have? One carbon, two oxygens, right?
Yeah.
Right? So let's start making combinations of a carbon molecule. So let's make COOs, COOs, COOs. So the first one can be a carbon-12 with one oxygen-16, one oxygen-17. The second one can be a carbon-13 with one oxygen-16, one oxygen-17. Then we can have a carbon-12 with 16 and 16 oxygen. Then we can have a carbon-12 with 17 and 17 oxygen. Then we can have a 13 with 16 and 16, and a 13 with 17 and 17, right? Is that all we can have?
Yes.
Okay, perfect. So we have 6 possibilities. Possibilities. Now, write down the formulae of all the different CO2 molecules. We're done with this part. Which molecule has the largest mass? So which one will have the largest mass? We just need to sum up all the isotopic masses. So 13, obviously the largest of the masses, so carbon 13 and oxygen 17. So a molecule with one carbon 13 and two oxygen 17 will obviously have the largest mass. One carbon 13, two oxygen 17. So 13 plus 17 plus 17 gives us 47. You can take out masses for each one of them, but it's useless because using common sense, we can discuss individual mass will be the greater one. The sum of that will also be greater. So this one turns out to be 45. This one's 46. This is 44. This is 46. This is 45. And this one is 47, the largest one. Okay. Any questions still here?
No.
Oh, a few definitions for relative isotopic mass, relative atomic mass, etc. that you have to learn. Now, this statement here, relative to 1/12 the mass of one atom of carbon-12, is something that we use in chemistry to compare two molecules. So, relative to 1/12 the mass of one atom of carbon-12 basically means that carbon-12's mass is 12, right? So 1/12 of 12 is 1. So they're basically saying the relative isotopic mass is the mass of one atom of the isotope relative to 1/12 the mass of one atom of carbon-12. So this is just a statement that they are using to compare the mass of a carbon atom and the mass of an XYZ atom that can be your relative isotopic mass for any atom, right? Now we can also say K uh okay, I could have used hydrogen in place of carbon as well. I could have said one part of one atom of hydrogen. And now hydrogen's mass is 1, which is why we don't use it because it's useless to use 1. So basically, this is just a statement of comparison for any XYZ molecule that has a relative isotopic mass. Okay, so we only use it when we're writing definitions. Okay, but this is necessary when you're writing definitions, so don't miss out on this. Then we have relative atomic mass, that is the AR. This is the weighted average of all the isotopic masses right? AR is the weighted average of all the isotopic masses, right? Because the formula is percentage abundance into isotopic mass for one isotope plus percentage abundance into isotopic mass of another isotope, and all of this over 100. So it's basically the weighted average of all the isotopic masses of all its natural isotopes again relative to 1/12 the mass of one atom of carbon 12. Then we have relative molecular mass. Now these last two definitions that I'm giving, relative molecular mass and relative formula mass, these two cannot be used interchangeably. Why? Let me tell you. Now, both of these are basically the sum of all the masses of each atom in a molecule. So for example, I'm talking about H2SO4. So this means 1 into 2 for hydrogen. Then for sulfur, it's 32. And then for oxygen, it's 4 into 60, right? So the sum of all of this is called the relative molecular mass. Relative formula mass is also sort of the same thing, but this is for covalent molecules. This is for ionic compounds. So examples of an ionic compound can be NaCl. NaCl's relative formula mass should be 23 for Na, and Cl should be 35.5. The total turns out to be 58.5. So NaCl's relative formula mass is 58.5, and H2SO4's relative molecular mass is 98. So when we're talking about covalent compounds, we always use the word relative molecular mass. And when we're talking about ionic compounds, we always use relative formula mass. Is this clear?
Can you repeat it one more time?
Okay. देखो, H2SO4 is a covalent compound, right? Right?
Yeah.
And NaCl is an ionic compound. So both of these, if I say calculate the mass of H2SO4 and NaCl, you're going to calculate it this way, right? For both of these, you're going to take out atomic masses from the periodic table and add all of them together, right?
Yeah.
So that's what I did. I calculated the total mass of each molecule. Now, when I talk about a covalent compound's total mass, I will refer to this value as relative molecular mass. And when I'm talking about the total mass of an ionic compound, I will refer to this value as relative formula mass. So the calculation is same, the concept is same, but the way you refer to both of these numbers is different. And why is it different? It depends on the type of molecule. So if you have a covalent molecule, you will say relative molecular mass. And if you have an ionic molecule, you will say relative formula mass. Clear?
Yes.
Okay.
Miss, how do you tell if one is covalent compound or ionic compound?
Oh, you don't know that? Okay. Let me, I think that is why you're confused. Okay. So there are three types of compounds. Covalent compounds, ionic compounds, and sorry, three. Metallic compounds. So covalent, ionic, metallic. Now, how do we differ between these three compounds? Covalent compounds, let's start with ionic. Ionic compounds, as the name suggests, are made up of ions, right? So if my molecule is NaCl, how do I know if it's an ionic compound? Because sodium makes an ion of Na plus, chlorine makes an ion of Cl minus. So a positive ion and a negative ion combine together to make an ionic compound. Okay? And when we're talking about covalent compounds do not have ions. ठीक है? Covalent compounds can be, now if I'm talking about carbon and oxygen, meaning CO2, right? Are these made up of ions?
No.
No, right? So I'm going to call this a covalent compound. Ionic compounds में total transfer of electrons takes place. And covalent compounds में sharing of electrons takes place. This is the major distinguishing factor between the two. Now I'll tell you what this means. So if I'm making a CO2 molecule, carbon comes here. I'm only making the outer shell. So one carbon and two oxygens, right? This is what a CO2 molecule looks like. Now, oxygen needs two more electrons. Oxygen is O2 minus, carbon is C4 plus or C4 minus, right?
Yes.
So one oxygen needs two electrons. So carbon gives two electrons to one oxygen. And carbon gives two electrons to another oxygen. So carbon gave, matlab shared two electrons with this one and two electrons with this one. And in total, carbon could share 4 electrons, right? So it's a win-win situation for carbon, right? Because carbon wanted to share 4 electrons. One oxygen wanted to share 2 electrons. And the other oxygen also wanted to share 2 electrons, right? So in this case, what are they doing? They are sharing electrons, right? But in the case of an ionic compound, if I look at NaCl, Na donates 1 electron, Cl takes 1 electron, right? So if I'm making an ionic compound, here's my sodium atom, Na plus, and here's my chlorine atom, which is a Cl minus. So sodium ke outer shell mein how many electrons do we have? Sodium's number is hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, neon, sodium. It's 9, 10, 11. Sodium is 11. And chlorine is
16 or 18?
I think chlorine is 17. Okay. So sodium's electronic configuration is 2, 8, 1, and chlorine's electronic configuration is 2, 8, 7, right? Abhi tak sab clear hai? Any confusion?
No.
No. So sodium has 2, 8, 1. So sodium has 3 shells and chlorine also has 3 shells. So 1, 2, and 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And chlorine has 17. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? So for sodium, it's easier to give up this electron and get 8 electrons in its last shell, right?
Yeah.
And for chlorine, chlorine needs 1 more electron for it to complete its outermost shell, right? So what happens during ionic bonding is sodium completely gets rid of this 1 electron and it gives this 1 electron to chlorine. So a total transference of electrons takes place, right? Electron has gone from here till here. They are not sharing electrons here, right? Sharing nahi ho rahi in ionic compounds. It has totally transferred, right? Now this electron is from sodium, right?
Yes. Miss, I have a question.
Yeah.
For ionic compound, in the
Hmm.
exam, they tell us which one has positive or negative charge.
As in, you mean sodium and chlorine?
Yeah, in the exam, will they tell us that sodium has positive
No, no,
charge?
they won't tell you. I remember I explained you about ions. Remember this?
Yeah.
So here magnesium's atomic number is 12, right?
Yeah.
So you're going to find out the electronic configuration 282, right?
Yeah.
You know how to find the electronic configuration, right?
Oh, okay. So then it's gonna be positive because it's gonna lose the 2 electrons at the end.
Exactly. So
Oh, okay.
Mg turns to be Mg2 plus. ठीक है?
Okay,
And
okay.
if I'm talking about nitrogen, so nitrogen's atomic number is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. It's 7. Okay, so nitrogen's electronic configuration is 2,
5.
5, right? So for nitrogen, it's easier to take in 3 electrons, right?
Yes.
Nitrogen's ion will be with a minus charge of 3 minus. So this is what a nitrogen ion is going to be, right? So how do you
Okay.
figure out if it's a positive ion, if it's a negative ion, or what number should be there with the positive or the negative? You look at the electronic configuration. And then you figure out if it's more than 4 electrons, if it's less than 4 electrons. This is how you see. So 3 electrons, Lena is easier than giving up 5 electrons, right? The smaller number, taking it is easier. So we say N3 minus. For magnesium, it's 2, 8, 2. So giving up 2 electrons is easier than taking in 6 electrons, right?
Yeah.
Okay, so this is how you check that.
Okay, miss. If an element has
Hmm.
four electrons in its outer shell, does it
Hmm.
gain or lose the electrons?
Okay, in this situation, it can be carbon, and carbon then has 2 different oxidation states. So carbon ka atomic number is hydrogen, helium, lithium, beryllium, boron, carbon. Carbon is 6, right? So carbon's electronic configuration is 2, 4. Now in this case, you'll be confused. Should it take in 4 electrons to make it 8? Or should it give up its 4 electrons to make it 8? In this case, we say that carbon's oxidation state is 4 minus or 4 plus. That is why carbon is usually in covalent compounds and not ionic compounds. So covalent compounds, it's always sharing of electrons, right?
Yeah.
So this is how carbon manages to share electrons with oxygen. It doesn't directly donate, it shares.
Okay, I get it now.
Okay. Just give me a minute. Okay. Okay, so we were talking about, is this clear till here? Ionic compounds and covalent compounds?
Yes.
Okay, now you know the difference between these two. Now coming back to this definition, so for covalent compounds, whenever we're talking about the total mass, it's called a relative molecular mass. And when we're talking about the total mass of an ionic compound, we refer to it as the relative formula mass. Okay, so relative molecular mass for covalent compounds, relative formula mass for ionic compounds. Correct?
Yes.
Okay. Now, in 9 minutes to go, I just give you a short introduction of what a mole is, and then we'll continue with this in the next class.
Miss,
Yes.
do I need to know the metallic compound or no?
Metallic may, it's just the element. For example, a metal lattice. Sodium is a metal, magnesium is a metal, aluminum is a metal. So they're not combining with each other. What this basically means is metallic compounds have metallic lattices. Now, what do I mean by a lattice? A lattice is a symmetrical structure. So for sodium, this is what a lattice looks like. It's a cube. So sodium has a +1 charge, plus, minus, minus, plus. So we have alternating charges in a metallic lattice. So they might just ask you in the exam to make a metallic lattice for either sodium or magnesium or aluminium. So what you need to make sure here is that you write the correct charges. For sodium, it's +1, magnesium +2, aluminum +3, and so on. So if I were to make one for aluminum, I would have said that instead of +1 and -1, I'll have +3 and -3 in my metallic lattice.
Okay.
Clear? Now make sure that these are alternating, minus with a plus. Any minus should not be connected to another minus. That will be wrong. So -3 connected to a +3, -3 connected to a +3, +3 connected to a -3, +3 connected to a -3, right? So there should be alternating signs. Okay.
Okay.
Okay. So in chemistry, if I'm talking about any substance, 1 mole of that substance always has this many particles, no matter what that substance is. So if I have a glass of water, I'm going to say that 1 mole of this glass of water has 6.02 into 10 to the power 23 atoms. 1 mole of this water. Now, if I have a basket of grapes, okay, I have a basket of grapes, and I say that 1 mole of these grapes contain 6.02 into 10 to the power 23 atoms. This is correct. This is correct. So 1 mole of anything, 1 mole of anything will always have 6.02 into 10 to the power 23 atoms. 6.02 into 10 to the power 23 atoms. Now 1 mole of H2O of water will also have 6.02 into 10 to the power 23 atoms. 1 mole of sodium will also have 6.02 into 10 to the power 23 atoms, and so on. Okay? Now, what is this number? 6.02 into 10 to the power 23. What even is this number? This number is called Avogadro's constant. Okay, and Avogadro's constant remains constant. It is a number, and this number is 6.02 into 10 to the power 23. You need to remember this number. Okay, and Avogadro's constant is denoted by the letter L. Now, if I'm saying that 1 mole of sodium is 6.02 into 10 to the power 23 atoms, what will be the answer for this? How many atoms will 2 moles be?
6.02 times 10 to the power 23, the whole times by 2.
Exactly. So what I'm going to do is I'm going to cross multiply, and my answer is going to be 2 into 6.02 into 10 to the power 23. And this will be my answer for this question. So there's a general formula for this. That is so this is exactly what we did, right? We did number of particles which you wanted as an answer equals number of moles into Avogadro's constant, right? So this is a generalized formula. Okay, to find the number of particles in whatever number of moles. Any questions still here?
No, miss.
Okay, perfect. Next class, we're going to start with most probably electronic configuration. Okay,
Okay.
take care. I see you in the next class.
Bye, miss.
Bye.